PYZ, I will explain the coordinate later. That is exponential j kr plus pi over 4, that is a strange number, and then square root 2 pi dot 8 pi kr and v theta phi, and then plus 0 exponential j k sine phi y plus j k cosine phi v. This is when theta is smaller than phi, and this is when theta is greater than phi, and v theta phi is some function in theta and phi, and the coordinates look like, okay, this is z, this is r, and this is y, and this is theta, and angle of incidence is phi. Okay, right, and the coordinate toward this direction is x. Okay. What does this mean? The sound pressure on y and z plane for a two-dimensional obstacle. In other words, the obstacle is infinite in x direction. Okay? Behaves as if the radiation, two-dimensional type radiation, therefore the spreading is proportional to square root to r, as we saw before, and exponential jkr type radiation. Okay, but that has two components. One is, and also directivity is related with the theta and the phi. But when theta is smaller than phi, that means what? When theta is smaller than phi, what does it mean? When theta is smaller than phi, this is when theta is equal to phi, that means we are seeing sound over here, right? But theta is smaller than phi, that means I am here, right? When theta is greater than phi, I am here, right? So when theta is smaller than phi, I can only see this. But when theta is greater than phi, I see this field as well as this field. Right? In this region, what I can see is the sound radiation from this, but in this region I can see that the radiation from this scatterer as well. Right? That's what this equation really says. Okay, suppose that I am saying over here, then the sound you can hear is the sound as if it is radiating from this edge, right? But when I say over here than what you will see, the sound radiating from the source. Okay? Alright? And what you will see is the sound first hit this wall, and due to impedance mismatch, there will be some scattering. So therefore, the sound is like you have many sources over here. Right? Right? Or maybe I will use this door. The sound is radiating from this edge, right? Sound is radiating this edge, right? Huh? Well, when I say over here, sound is coming and reach your ear, right? When I different, huh? When theta and phi is different, the radiation pattern should be different. Okay? So, having that idea in mind, somebody devised this kind of scatterer to have less diffraction. Less diffraction. Right? Well, so therefore, when you go to the highway, and when you see the some residential area along the highway, you will see sound barrier, right? Some sound barrier has not just the straight wall, but that has somehow the barrier at the end has some angle, right? So that angle, get the idea from this kind of diffraction phenomena. But strictly speaking, that angle has to be related with the wavelengths, right? Therefore, what we first have to know is what is the frequency content of noise is. And then we can find out the sound radiation due to diffraction, maybe using this formula, and we can calculate dB down, how much dB down we will obtain over here. That sort of thing can be done. Okay? Therefore, we devised a very practically very useful formula for measure that measures the primary physics that is associated with the diffraction, that is Fresnel number. And I will explain the Fresnel number. Okay? For example, let's consider this kind of physical situation. I have ground and I have world. Okay? And suppose I have a source over here. And suppose we have listener.